Hello. We are officially in the last portion of Calculus 3. We're starting with surface integrals in 16.7, and then we'll follow up with a couple of theorems that make surface integrals a little bit easier. So what a surface integral does is it calculates, let me get a pen here, it calculates the integral of a function little f or vector field big F over a surface big S. Okay, we're going to be starting off with surface integrals of scalar functions to begin with, and then we'll have to cover a few topics before we can get to the second part of this, which is where we'll look at surface integrals of vector fields. But when we're working with a surface integral of a scalar function, we've got like some surface that we're working with like this, and we've got little patches of ds on our surface, and then we've got maybe some function little f of x, y, z, and we're integrating over these little patches of surface, and then we're going to have an infinite number of those and add them all up, and we're going to have an integral. So when we work with the surface integral of a scalar function, things are going to be pretty straightforward. And when we start working with the surface integral of a vector function, we're going to have to worry about this thing called an orientable surface. But we'll talk more about that when we get there. For now, what we have is we're going to be integrating a function f of x, y, z over some little bits of surface area. So d big S is the differential of surface area. And we just finished 16.6 where we covered surface area, and we just learned that ds is going to equal the magnitude of r sub u cross r sub v dA. So that was in 16.6, that magnitude of the cross product, that was our integrand. Now it's our differential. So we're integrating over that, and we're integrating this little function, little f of x, y. Now here's the deal. We have ds, and ds is in terms of a parametric function, r of uv. R of uv has its first partials taken and a cross product found and a magnitude of that found. Now, we have a double integral over the surface, because it is a surface integral, and a surface, once it's parametrized, only has two variables. We have a problem. Little f of x, y, z is a function of three variables. So we need to, in a sense, parametrize our little function by inserting the vector r of uv into it. And so what I mean by that is, if we look at these steps, first we parametrize S with a two-parameter vector function, r of uv. In the second step, what we do is we evaluate our scalar function, f of x, y, z, at r of uv. And so remember that r of uv has components x of uv, y of uv, and z of uv. We call them the x, y, and z components. So we're going to take those components, and in our scalar function, anywhere there's an x, we're going to put in the x component from the parametric surface. Wherever there's a y, we're going to take the y component from the parametric function, and the same for z. So then we're going to have, basically, it'll be f of r of uv. Once we have our scalar function fixed at r of uv, then we're going to calculate d big S, which is going to be that magnitude of the cross product of the first partials of r of uv. And then we're going to put it all in an integral. So here's the translation of the double integral over S of f of x, y, z, d big S. And I keep saying d big S because we just got done working with line integrals, and we were dealing with d little s. And so we need to be able to know the difference between the two. So with d big S, remember it's little patches of surface area, right? And so ds and the magnitude, those are both little patches of surface area. Okay. So every time we're asked to calculate a line integral of a scalar function, this is the format that we're going to use, unless, of course, our surface can be described by some explicit function. So we're coming back to this explicit function thing because we still have that surface area patch, and we found that there were two ways to do it depending on whether we had a parametric function, r of uv, or we had an explicit function that made things a little bit easier. So if we have a situation where z is equal to g of xy, right? Z is an explicit function of g of xy, then our ds will be calculated just using the square root of the sum of squares of 1 plus g sub x squared and g sub y squared. Similarly, if we had y is equal to an explicit function of x and z, then our ds is going to look a little bit different because the parameters will be x and z, so we'll need first partials with respect to x and z. We'll square them, we'll add them to 1, and we'll take the square root. And then similarly, for the last one, we have if x is a function of y and z, then y and z are the parameters, and so then we need to have first partials of those, square them, add them to 1, take the square root, and that will be our ds. Okay? Cool fact is if you can imagine little f of x, y, z is equal to 1, then a line integral or over s of f of x, y, z d big S is just equal to the line double integral over s of 1 ds. But remember, ds is going to give us that magnitude of the cross product of r sub u and r sub v dA, which is just going to be surface area. So I say that to remind you of, like, whenever we're working with a new integral, typically we have an integrand that is not 1, but what happens when it is 1? And usually it relates to something we've already done. And so in this case, if our integrand is 1, then we are working with surface area again. Similar case that we saw in line integrals, if we were taking the line integral and the function that we were working with was 1, then the line integral was equal to the arc length. Okay, because in line integrals, we are always integrating over the arc length. All right, another thing for you to pay attention to is the notation here. So make a big note. In a line integral, and this is all for scalar functions, okay? So in a line integral, we had the line integral over c of f of x, y, z, d little s, and a surface integral looks really similar, but it's a double integral over big S of f of x, y, z, d big S. So I kind of stress the size of my s's right there, since lowercase s and uppercase s look the exact same. Okay, so let's look at some examples. That's really all the theory there is behind that. We're just integrating over patches of surface area. Let's see what we end up getting. Here we're supposed to set up the surface integral below, where S is the surface with the vector equation r of uv equals a vector with components 2uv, u squared minus v squared, and u squared plus v squared. And then we've got a domain of integration. That's what this last piece is telling us. U squared plus v squared is less than or equal to 1. That's going to be our domain. Okay, so we have our x component, y component, z component. We have to remember, if we're asked for a surface integral, what we need to find is a few things. First of all, we have to identify f of r of uv, because that's going to be our integrand. X squared plus y squared is our f of x, y, z. So we've got to, everywhere there's an x, replace it with the x component from r of uv. So x squared gets replaced with 2uv all squared, plus y squared gets replaced with the y component. The y component is u squared minus v squared. So I'll put that all in a square. Okay, and then we need to go ahead and expand that and simplify that. So this gives me 4u squared v squared plus u to the fourth minus 2u squared v squared plus v to the fourth. And then stuff simplifies a little bit. We get u to the fourth plus 2u squared v squared plus v to the fourth. Okay, that's my f of r of u, v. Next, what we need is ds. Remember, ds is going to be the magnitude of r sub u cross r sub v dA. So that means I need to find r sub u and r sub v, and then I need to find their cross product. So wish me luck here. R sub u, the first component is going to be 2v. The second component is 2u. The third component is 2u. R sub v, the first component is 2u. The second component is minus 2v. And the third component is 2v. So I did my little trick again. I lined up my r sub u and my r sub v so that they're set up perfectly so I can kind of see what my cross product should look like. R sub u cross r sub v can then be calculated fairly straightforward. So for my I component, I have 2u times 2v minus a negative 2v times 2u. For my j component, I have a minus, and then in parentheses, I have 2v times 2v, which is 4v squared, minus 2u times 2u, which is 4u squared. For my z component, I get, or my k component, I get 2v times negative 2v, which is negative 4v squared, and then minus 4u squared. Okay, I just have to rewrite that one more time. I get 4uv plus 4uv. So I get 8uv in the first component, and then I get 4u squared minus 4v squared in the second component, and then I get minus 4v squared minus 4u squared. Okay, that is my cross product. Not done yet. Now I need to get the magnitude of that. To get the magnitude of my cross product, it's going to be the square root of a whole lot of stuff. All right, squaring the first term gives me 64u squared v squared plus 4u squared minus 4v squared all squared plus minus 4v squared minus 4u squared all squared. This is going to take a little bit of work here. All right, so we have the 64u squared v squared plus, and I have to FOIL each of these out. I get 16u squared minus 4 times 4 is 16 times 2 is 32u squared v squared plus 16v squared plus, and I FOIL the last term, I get 16v to the fourth. You know what? Hold on. I squared my 4u squared. I should have gotten 16u to the fourth. And I squared my 4v squared, and I should have gotten 16v to the fourth. Phew, I'm glad I caught that now. Okay, so I've squared my minus 4v squared, and I got 16v to the fourth, which is good. Negative 4 times negative 4 is 16 times 2 is plus 32u squared v squared, and then plus 16u to the fourth. Okay, I need to gather some like terms, see if anything goes away. I'm noticing the minus 32u squared v squared and the plus 32u squared v squared. And I'm noticing I can combine a couple of things, the 16u to the fourth, and there's another 16u to the fourth. All right, let's go ahead and get these all together. This is equal to, I have 32u to the fourth plus 64u squared v squared plus 32v to the fourth. Everything has a 16 in common, and really everything actually has a 32 in common. So I'm going to factor out a 16 and a 2. I know that seems a little strange. You'll see why. So I'm going to factor out a 16 and a times 2 and leave behind a u to the fourth plus 2u squared v squared plus a v to the fourth. Now the 16, I can take the square root of that. And technically I can go ahead and take the square root of 2 as well. So I'll get 4 square root of 2. And then I have the square root of, it looks like that's a perfect square trinomial, and it factors as u squared plus v squared all squared, which means I can take the square root of it. So finally, we have 4 square root of 2 times u squared plus v squared. All that work to get my differential. Okay. All right, so let's see, what do we want to do here? I'm going to go ahead and put all of this into my, my integral. All that work. So when we get to the integral, we're looking at the double integral over s of x squared plus y squared d big S is equal to the double integral. The x squared plus y squared, we got to go back. Let me see what that is. Oh, you know what? I'm looking at it. U to the fourth plus 2u squared v squared plus v to the fourth, that factors. And I noticed it before, but I didn't do it because I wasn't sure what ds would be. Now that I know that ds is very similar, I'm going to go ahead and factor this perfect square trinomial. It is u squared plus v squared all squared. So that is our f of r of uv. So I'm going to put that in to my integral. U squared plus v squared all squared. That's replacing the x squared plus y squared. ds is 4 square root of 2 times u squared plus v squared. And then I have my dA or du, dv, or however this is going to be done. I'm going to write it as dA for now. And then I want to recall our domain was given to us as, let me recall exactly how they wrote it. U squared plus v squared is less than or equal to 1. So that region is all the UV values inside of the unit circle. That's going to be our D. Okay. So we should probably be switching over to polar because we have a polar region. And in the polar region, it's a unit circle. So R goes between 0 and 1, and theta goes between 0 and 2 pi. And u squared plus v squared is equal to r squared, while r travels from 0 to 1. Okay, let's go ahead and take care of this. Last thing, dA will be equal to r dr d theta. Okay, finally, this is equal to the integral from 0 to 2 pi, the integral from 0 to 1. I've got a 4 square root of 2. I have u squared plus v squared. I have 3 of those, so that's cubed. So I'm going to replace it with an r squared all cubed. And then the dA is r dr d theta. There's a lot of work just to get to there. Okay, so r squared cubed is r to the 6th, and then there's another r, so I have an r to the 7th. I'm going to break this up because I have no thetas in here, and my integrand bounds are all constants. So I can look at this as the integral from 0 to 2 pi of d theta times the integral from 0 to 1 of 4 root 2 r to the 7th dr. And then I'll take the integrals of each at the same time. So this gives me theta from 0 to 2 pi from the first one times 4 square root of 2 over 8 r to the 8th from 0 to 1. I get 2 pi from the first one, and the second one simplifies to be root 2 over 2 times 1 to the 8th minus 0 to the 8th, which is just 1. And this finally simplifies to pi square roots of 2. And that's it. That is the value of the surface integral over that surface area. Okay, so it's a lot of work for the setup and not a whole lot for the actual integrating. Let's look at another example. Oh, I gave myself 2 pages. Well, some of you might need 2 pages, so that's good. All right, so for this next one, we're asked to set up the surface integral. And this surface integral is the double integral over s of y squared z squared ds, where s is the part of the cone. So they're describing our surface right now. It's the part of the cone y equals the square root of x squared plus y squared, where y goes from 0 to 5. Okay, so let's see. How are we going to do this? Well, let's see. We have an explicit function, so we should definitely take advantage of that. That's like the best part. So in an explicit function, we're looking at x and z get to be themselves, and then y is going to be, so if we are going to parameterize it, x and z are the parameters, and then we would have x gets to be x, y is the square root of x squared plus z squared, and then z gets to be z, okay? But I don't want to take r sub x, r sub z, and then do a cross product, and then find the magnitude of that and take all of those steps. I would much rather use, so it's easier to use, ds is equal to the square root of 1 plus, and we're going to say this is del y del x all squared plus del y del z all squared dA. Okay, so that means we're just going to go ahead and find those first partials, square them, and add them. Okay, so del y del x is equal to, and we have a square root, so we've got a power rule, 1/2 times x squared plus z squared to the negative 1/2 times 2x, which simplifies to x over the square root of x squared plus y squared. Del y del z is very similar. We'll get 1/2 times x squared plus z squared to the negative 1/2 times 2z, and that simplifies to be z over the square root of x squared plus y. I don't know why I keep writing y squared. It should be z squared, guys. Okay. All right, so now I'm going to square both of those and pop them in and add them to a 1 under the square root. So we have the square root of 1 plus x squared over x squared plus z squared plus z squared over x squared plus z squared. If I add those two fractions, since they have a common denominator, I get the square root of 1 plus x squared plus z squared over x squared plus z squared. This is just the square root of 2. Because we have x squared plus z squared over x squared plus z squared is 1. Add that to a 1. We just get the square root of 2. Okay, the next thing that we have to do is, let's see, f of x, y, z is equal to y squared times z squared. But we have an explicit function for y. So f of x, this is going to look weird, square root of x squared plus z squared, and z. So everywhere there's a y, I have to replace it with that square root of x squared plus z squared. So I'm going to do that. Put in the square root of x squared plus z squared and square it, and then times z squared. Well, the square and the square root go away, so we just are left with x squared plus z squared all times z squared. And of course, that can simplify. We can go ahead if we want, and we can distribute. But let's see about our domain of integration, how we're going to deal with this. So let's see. We have y is going from 0 to 5. And we're dealing with a cone. I should draw this. So at the origin, we just have a dot. And as we move out and we get to 5, that's going to be the end. So y is just going from 0 to 5. But for all levels of y, we have different size circles. Okay? So we could think of y as like a radius, right? Because we have y is equal to the square root of x squared plus z squared, and y squared is equal to x squared plus z squared. And we are told that y goes between 0 and 5. So since y is between 0 and 5, we could say that y squared is between 0 and 25, which means that our circle, the x squared plus z squared, is a whole bunch of circles with radii that vary between 0 and 5. Okay? So we can switch our we can switch our bounds over to polar, because we're going to be looking at the xz plane now, circles. We have figured out what our, by using the bounds on y, we're able to figure out what the bounds on our radius are. Okay, so the bounds on y serve to give us the bounds for our radius. Okay, so now we know that r is going to go from 0 to 5, and these are going to be full circle, and theta is going to go from 0 to 2 pi. Okay, now we have an axis where, well, it's an xz axis, and if we draw it in the positive way, let's see. Well, this is really weird. Okay, so if we were standing on the y-axis and facing the xz plane, the positive x direction is on the left, not on the right. So I kind of need to draw it that way in order to make sure that I'm getting the right parametrization here. And I'm being picky about this more for when we are dealing with surface integrals over vector fields. Right now, actually, the signs that we get will be fine. We're not worried about direction that we go around, but we should draw our axes correctly, okay? So on our axes, we have circles of radius 5, or up to 5. We have all the space in between, though. Okay? And so on this circle, we can define x to equal r cosine of theta, and y to equal, not y, z to equal r sine of theta. Okay, so now we have replacements for stuff in our integrand as well. Okay, Let's figure out where we were. We have a double integral over S of y squared z squared ds is going to equal, and let's find all those parts that we found, okay? The y squared z squared, that's f of x, y, z, and we went ahead and we fixed it with our explicit function. And so now it's going to be x squared plus z squared times z squared, okay? And then we have our ds, which we found part of that. So we could tack on that from this, ds is equal to the square root of 2 dA. So we'll put in that square root of 2 and our dA. Okay. Now that we have that taken care of, we can go ahead and do our switch over to polar coordinates. Okay, so right now I'm just keeping this generic. It's integrated over the region D with respect to dA, and I worry about my bounds now that I have everything written out. So our circular relationship, x squared plus z squared, that's going to give us r squared. Our bounds, let's see, we've got 0 to 2 pi. We have 0 to 5. We have an r squared from the x squared plus z squared. The z squared that's standing alone on the outside, that's r squared sine squared of theta. Then we have our square root of 2, and dA will be r dr d theta. Okay, now we've got to put that all together. We need to get our r's together and our thetas together. I'm going to split this up into two integrals again. So I have 0 to 2 pi. I have my sine squared of theta d theta. And we have 0 to 5. Let's see, I have r squared, and r. So I have r to the 5th, and then I have a square root of 2, r to the 5th dr. Okay, we cannot integrate sine squared directly. We must do a power reducing formula. So we have to recall that sine squared of theta is 1/2 minus 1/2 cosine of 2 theta. So I'm going to go ahead and make that replacement. So this is equal to the integral from 0 to 2 pi of 1/2 minus 1/2 cosine of 2 theta d theta. I can go ahead and integrate my r. I get square root 2 over 6 r to the 6th power, going from 0 to 5. I'm going to need a calculator for this. I'm just going to get that out really quick. I'm going to go ahead now and for the left integral, I'm going to integrate with respect to theta. This gives me 1/2 theta, and then it'll be minus 1/4 sine of 2 theta, going from 0 to 2 pi. And then 5 to the 6th power is 15,625. And then minus 0. Okay, now evaluating a sine of 2 theta at 2 pi is going to give me 0, and evaluating it at 0 is going to give me 0. So what I get from here is 1/2 times 2 pi minus 0, and then minus 0 minus 0. So not a whole lot of contribution, but there is something. And then times 15,625 square root 2 over 6. Okay, and we are almost done. The 1/2 times the 2 pi just gives me a pi. My final answer is 15,625 square root 2 pi over 6. That is the value of the surface integral. Okay, again, there were a whole lot of steps there. It was really easy to get lost in what we're doing. You may go with the parametrization R of xz and find the first partials and find a cross product. I took advantage of the explicit function and just went ahead and directly calculated my ds without the need for a cross product. after we found the square root was going to be just the square root of 2. Then we took our function f of x, y, z and plugged in our parameters. And then we had to deal with the bounds of integration. So that was this section right here. You know, sometimes it's good just to label stuff. This right here was the integrand. All of this right here was the differential. Just all the parts that we have to find: differential, integrand, bounds. And then finally we can plug stuff in and realize we need to switch our bound, or we need to switch to a new system and go to polar coordinates. Okay, again, I gave 2 pages in case you need extra paper. All right, so this one I'm definitely not doing in class. We're doing this today. All right. We're supposed to evaluate a double integral over S of z ds, where S is the surface whose sides S1 are given by the cylinder x squared plus y squared equals 1, whose bottom S2 is the disk x squared plus y squared is less than or equal to 1, and whose top S3 is the part of the plane z equals 1 plus x that lies above S3. Okay, let's see. So our function is just z. So we're just integrating f of x, y, z equals z. But our surface is not so nice. Okay. Our surface has a whole bunch of sides. It has 3 sides. The first one is going to be the cylinder. X squared plus y squared is 1. So I'm going to start drawing this. And I'm not going to complete it. I'm just going to draw this portion of it for now. And I'm going to go ahead and put it on an XYZ octant. Okay. So S1 is the cylinder. Okay, that's the outer portion of the cylinder. Okay, it's vertical. S2 is the disk that is on the bottom. So that's S2. And then S3 is going to be the part of the plane that lies above. This is a typo. It shouldn't be above S3. It should be above S1, where S1 is a cylinder. So I need to draw that plane z equals 1 plus x. And that plane will be coming. That's interesting. So let's make this my negative y, and this will be my positive x, just to make it easier for me to draw this. Because z equals 1 plus x has intercepts on the x-axis and the z-axis. I'm trying to make this convenient for myself. That's really all that's going on here. So this is 1. I'm going to call this 1 as well. And I'm going to erase some of what I've drawn here, my sides. I'm only going to have my bottom left right here, but I'll get them back in. Okay. My left side, I'll go ahead and keep that in, maybe a little bit shorter. Okay. I have this plane right here. Z equals 1 plus x has intercepts on the z-axis at 1 and on the x-axis at 1. Is that right? No. No. My x-intercept is going to be at -1. Hang on. Okay. Hang on. I hate making mistakes on a video, but it's fine. It's fine. So this will be my negative x and this will be my y. Okay. And then this is at -1. Okay. This is all going to work out. I just have to make sure that my x and my y axes are staying in the correct order and that I don't suddenly like flip-flop them. Okay. So I'm really just spinning my octant around to the view that is convenient. I really should have just been more careful here and said if x is 0, z is 1, and if z is 0, then x is -1. Then I would have had my intercepts much better and faster. Okay. All right, back to the plane. Z equals 1 plus x. So my cylinder is going to go up to the plane in all regions, but then it's gonna be cut off, and the shape that will form at the cutoff will be circular because we were working with a cylinder after all. Okay, so this is kind of the shape that we're working with. All right. We have 3 surfaces. That means we have 3 parametrizations that we have to deal with. Okay, so S1 is going to be the lateral surface, that's the outer surface, of the cylinder. Okay. The parametrization, and let's go ahead and state what that is, x squared plus y squared is equal to 1. The parametrization, well, with that we could say that, parametrization. We could say x is going to equal 1 cosine of theta, and I say 1 because it's a unit circle. Y is going to equal 1 sine of theta. Z is not involved in that equation of the cylinder, so Z just gets to hang out and be Z. Okay? Now, we need bounds for these. We are going to have bounds for Z and for theta. Okay? We're looking at R of theta Z is cosine of theta, sine of theta, and Z. And so the bounds on theta, those are pretty simple. We are still going all the way around, so we can say theta goes from 0 to 2 pi. Z, we know, is going from 0 to 1 plus x, the equation of the plane. But we're no longer working with x as an x. We're working with x as cosine of theta. So this means that Z is between 0 and 1 plus cosine of theta. Okay, so those are going to be the bounds for Z and theta. I need to get my cross product. So let's see. This gives us bounds. Let's go with R sub theta. R sub theta is going to give me, I look at my R of theta Z. The first component is cosine of theta. The derivative of that is minus sine of theta. The derivative of sine of theta is cosine of theta. And the derivative of Z with respect to theta is 0. R sub Z is very nice. It is 0, 0, 1, because Z only shows up in the third component. So then we can find R sub theta cross R sub Z, fairly straightforward. Got that same trick where I've got things lined up nicely for myself. And it looks like the only contribution I'm really going to get is from my I component. From my I component, I get cosine of theta minus 0. And then from my J component, I do get a little bit as well. I have minus, and then I have a negative sine of theta minus 0. And for my K component, I get 0 minus 0. And so my cross product is just cosine of theta, sine of theta, 0. So the magnitude is pretty easy then. The magnitude of R sub theta cross R sub Z is the square root of the sum of squares. So cosine squared of theta plus sine squared of theta plus 0 squared. This just gives me the square root of 1, which is 1. Okay, so my surface integral we're looking at the double integral over S1 of z ds1 is going to equal the double integral. We're going to, z can stay z, that's what it is, times the ds. ds1 is going to be 1 dA. And then we are going to be switching over to the bounds that we have. We parametrized, so we have dz, d theta, so we're not going to write dA. We're going to go ahead and say, okay, we've got a double integral. Theta goes from 0 to 2 pi. Z goes from 0 to 1 plus cosine of theta. And then we have z, and then we have dz, d theta. Okay? Now, from here, it's not too bad. We can go ahead and integrate with respect to z. Get the integral from 0 to 2 pi of 1/2 z squared from 0 to 1 plus cosine of theta. And then when we're done with that, we'll deal with d theta. This is equal to the integral from 0 to 2 pi of 1/2 times 1 plus cosine of theta all squared d theta. So I'm going to have to expand that, and then I'll be able to maybe use some trig identities. All right, I'll pull the 1/2 out. Integral 0 to 2 pi, 1 plus 2 cosine of theta plus cosine squared of theta, d theta. We have to use the power reducing formula. Cosine squared is 1/2 plus 1/2 cosine of 2 theta. So that was a power reduction, not an integration. Okay, this is just a trig identity to make it so we can integrate. So I'll rewrite one more time. It's the integral from 0 to 2 pi. Oops, almost lost my 1/2 on the outside. All right, we have our 1 plus 2 cosine of theta plus 1/2 plus 1/2 cosine of 2 theta, d theta. All right, got my 1/2 on the outside. The 1 plus 1/2 is 3/2, and when I integrate that, I get 3/2 theta. The 2 cosine theta, the antiderivative is 2 sine theta. The 1/2 cosine theta, the antiderivative is plus 1/4 sine of 2 theta, and we're going from 0 to 2 pi. The sine and the sine of 2 theta will both be 0 at 0 and at 2 pi, so we are really only going to get any contribution from the 3/2 times 2 pi. We get plus 0, and then minus a whole lot of 0. So this finally gives us an answer of 3 pi over 2. That's just for S1. We still have S2 and S3. Okay, let's see what happens with those. So now we're going to go on to S2. And if you recall, I'll go up to the top and recall for us. S2 is the disk. X squared plus y squared is less than or equal to 1 in the plane z equals 0. Okay? So it's x squared plus y squared is less than or equal to 1, where z equals 0. Okay, this makes life nice. The double integral over S2 of z ds2, where z is 0, is just the double integral of 0 over s ds2, which is just going to give us 0. Okay, so we're done with S2, thank goodness. All right, we have S3. S3 is that top surface, which was the plane. Z equals 1 plus x. We have an explicit function. if z is equal to a function of x and y, which is just 1 plus x. Okay? That's a nice thing. So when we, if we think about what our parametrization is, then x gets to be x, y gets to be y, and z is just 1 plus x. Okay? Now, when we use the explicit function, we should go ahead and use the fact that ds3 will be the square root of 1 plus f sub x all squared plus f sub y all squared dA. Okay? F sub x is just 1. Right, so let's go ahead and calculate those. F sub x is going to equal 1. There is no y in there, so f sub y is 0. And that makes this even nicer. So I plug everything in. I get the square root of 1 plus 1 squared plus 0 squared dA, which is just the square root of 2 dA. So this is our differential. Okay. Then for our integrand, we have z gets replaced by 1 plus x. Okay, so it looks like we are just about ready. We've got the double integral over S3 of z ds3 is equal to, let's see, we have the double integral of 1 plus x, and then we get a square root of 2, and we have a dA, and we have a domain of integration. We've got to figure out that domain of integration. So it turns out that if we go back up to our drawing, although we are dealing with a plane, the plane is cutting off a slice on our cylinder. And so we're not taking the part of the plane that's outside of the cylinder. We're just taking that round. It's a slanted round region. But if we project that onto the XY plane, we're just going to get a circle of radius 1. That's it. So the projection, let's see, how do I want to do this? The domain of integration, project the slanted circle from the intersection of the plane and the cylinder onto the XY plane. So on the XY plane, we simply get a circle of radius 1, which means that we're going to go ahead, since this is X and Y, we're going to go ahead and we're going to let X equal cosine of theta, 1 times cosine of theta there, and Y will be sine of theta. Sorry, I'm missing my R's here. I have R cosine of theta, and I have R sine of theta, because we are taking the entire region inside to integrate over. Okay, and then R has to go from 0 to 1, and theta has to go from 0 to 2 pi. Okay, so I can go ahead and pop all this into my integral. Now I'm looking at the double integral. I have 0 to 2 pi. I have 0 to 1. I have a square root of 2. I have 1 plus r cosine of theta. And then from the dA, I have r dr d theta. Okay. So let me go ahead and rewrite this so that things are combined the way they need to be. This is the square root of 2 integral 0 to 2 pi integral 0 to 1 of r plus r squared cosine of theta dr d theta. Now I cannot break up my integral this time. You know, I've been doing that whole product thing, and I can't do it because I've got a sum of things going on here. So I just have to go ahead and integrate with respect to r. So I'll do that. Square root of 2, integral from 0 to 2 pi. Antiderivative of r is 1/2 r squared. Of r squared is going to be 1/3 r cubed. The cosine of theta is merely a constant hanging out. We're going to evaluate this from 0 to 1. And then after we evaluate, we'll integrate with respect to theta. So evaluating at 1 and at 0, well, at 0 we get no contribution, and at 1 we get square root 2, integral from 0 to 2 pi of 1/2 plus 1/3 cosine of theta d theta. Okay, so we get the square root of 2 times 1/2 theta plus 1/3 sine of theta from 0 to 2 pi. Sine of theta at 0 and at 2 pi is 0, so I only get contribution from the 2 pi when I evaluate it at the 1/2 theta. I just get a bunch of plus 0, minus 0 otherwise. And this finally gives me pi square roots of 2. Okay, we're not done. So the original integral was a double integral over s of z ds, and it is equal to the double integral over s1 plus the double integral over s2 plus the double integral over s3. From s1, we got 3 pi over 2. From s2, we got 0. From s3, we got pi square root of 2. So our final answer, we could write it as pi times 3/2 plus square root of 2. And that's it. That is the value of the surface integral for when f of x, y, z is z, and we're integrating over these 3 surfaces. Okay, that's all I'm going to do for this video. 16.7 is a long one. So if you have any questions about surface integrals of scalar functions, please do reach out.